Now, today we will finish chapter 2, and I'll also some and let me get rid of this one here. Oh, it went to the beginning. Strange. Okay. It goes back to the beginning. I don't know why. Okay, let me look at this. Okay, now energy conversion efficiencies. So far in this chapter, we learned what energy is. And basically, the substances have internal energy, the energy associated with the molecules, their kinetic and potential energies because of their chemical bonds, which is the potential energy, or the molecular activity, like vibrations inside or motions, it is the kinetic energy. The sum of it is internal energy, and we call this the microscopic energy. And we also have, let's say, the system may be moving, the velocity may be changing, elevation may be changing, so it may have potential and kinetic energy if it is relevant. And then last time, we talked about the conservation of energy, and it is basically during a process, first you identify the system, and then energy coming in minus energy going out is equal to the energy change. Okay, so just logic. It is just like a bank account. If let's say you deposit some money into your bank account, and then you withdraw some cash, okay, the difference is the change in the balance of your account. So energy is that way. Simply whatever goes in minus whatever goes out is equal to change. Of course, here the mechanisms of energy transfer are it can be heat transfer if it is due to a temperature difference. It can be work if it is a force acting to a distance, or it may be mass. Anytime enters a system, okay, energy enters with mass. And when mass leaves, again, energy leaves with mass. So these are the three mechanisms there, okay? So the first of thermodynamics, or the energy balance, is simply balancing this out to make sure that energy is accounted for. That is, you don't destroy any energy and you don't create any energy. Because if you do that, obviously your result will not be correct. Okay? Now, efficiency is associated with some conversion processes. Energy is converted to from one form to another form, often, very often, in fact. Usually, this process is. Now, how do we define efficiency? Well, there are so many kinds of efficiencies, okay? So the general definition is desired output, whatever you want out at the end, and what is entering. The ratio is the efficiency. This is what you want to get out, the output, and then this is what you have to put in. Okay, of course, you would like all the input to be converted into output. In that case, the efficiency would be, yes?
May I interrupt you?
Yes.
I think we can't see slides.
You can't?
We can see slides. If you share that, we can see both of us.
Okay. The system does. Let me see. Okay, so you see the slides now?
Yes, sir.
Yes, sir.
We can see now.
Okay. Mehmetcan can simply cut that part out. Since now we have the slide. Energy conversion efficiency, okay, is simply associated with the conversion of efficiency process and how efficient that process is. You want to convert energy from one form to the other. Ideally, you would like all the energy, which is our input, to be converted into desired form of energy. If that happens, efficiency is 100%. But it is not the case most of the time. Therefore, we define efficiency. The general definition is you have, let's say, some energy input. You want to convert it to what? Some kind of output. Okay. We call it the desired output. This is the required input. Conversion efficiency. Many of you have water heaters in your homes. Okay. And let's say this is electric water heater, or it may be natural gas water heater. Definitely we have some energy input, right? This can be electric, or this can be natural gas. What is entering here? In the case of natural gas, chemical energy is entering. It is the amount of energy released when the gas is burned. In the case of electricity, simply electrical energy is entering. Okay. At the end, what do we want? We want hot water, which is thermal energy. Cold water will enter. Okay. Let's say cold water. It will be heated here, and then hot water will leave. And the difference of the energy of water between inlet and outlet is the amount of thermal energy, which is given as output, as useful energy, and the amount of energy which as electricity or natural gas chemical energy, it is the input. If you take the ratio, that is the efficiency of the water heater. If it is 100%, okay, that means all the energy which enters as electricity or chemical energy is now in water here, in hot water, as thermal energy with no loss. But it doesn't happen. At the minimum, this is the water heater, you have some heat loss here. And in the case of natural gas, you have combustion and you have the flue gases. The hot gases are leaving, unless it is a very efficient heater there, condensing the water vapor. And if you look at the values, efficiencies, let's say for ordinary heaters can be as low as like 55%. For electric water heaters, they can be like 94%. Okay, these numbers are a little old, so they may even be better today. If you have condensing heaters, then the gas heaters also will have very high efficiency there. Now, how do we deal with chemical energy and the combustion process and the combustion equipment? It can be like the car engines, it may be power plant where you burn coal, the boilers, it can be anything. That is where you burn fuel. You have combustion. Combustion means chemical energy being released as thermal energy there. Okay. And normally we define the combustion efficiency or efficiency of the combustion equipment as the useful heat supplied, okay, divided by the heating value of the fuel burned. Now, how do you determine this? You can simply pick it up from the tables. That is heating values of all the fuels, chemicals, whatever. They are measured in the labs and they are listed in the tables. You find it very easily. It is the heating value. So no matter what you are burning, you can find it. If not, you can take it to the lab. It can be measured very easily if we have something unusual. And after the combustion, you deliver some thermal energy. You have high temperature gases there. And that will be the combustion efficiency. Okay. Now, what is the heating value of the fuel? Since it is used in the denominator here as a heating value, it is the amount of heat released, okay, when a unit amount of fuel, like 1 kilogram or 1 cubic meter of fuel is at room temperature is completely burned and the combustion products are cooled to the room temperature. So let me explain here. Let's say we have gasoline. Okay. Yeah, you take 1 kilogram gasoline at room temperature, and then you take enough air, okay, again at room temperature here. You burn them in the combustion chamber completely, and you transfer the heat so that the combustion gases leave also at room temperature. And here there is no unburned fuel. The amount of heat released, and how can you measure that? You put this, let's say, in a water tank, okay? The amount of water, and all the heat will be transferred to water. You can measure the temperature rise of water, then you can calculate this, okay? In the case of gasoline, if the combustion gases are cooled to 25, but H2O is in the vapor form, we call this the lower heating value. If H2O is in liquid form, and how can it happen? The vapor condenses again at 25 degrees, and all the heat of the station is also transferred to water. Then it is called higher heating value. Therefore, fuels have two heating values. One is lower heating value, the other one higher heating value. When the water in the combustion gases is a vapor, so H2O is in the vapor form, it is called the lower heating value. When H2O is completely condensed, okay, then it is the higher heating value. The lower heating value, as you see here, is about 44,000 kilojoules per kilogram. The higher heating value is about 47,300 kilojoules per kilogram. But of course, when we say gasoline, it is anything but certain. There are so many different gasolines. The gasoline has like maybe 20, 30 different hydrocarbons in it, and the composition can be different, and these numbers may change depending on where you buy the gasoline there. But on average, this is what you should expect. Okay, so what is the difference? 44,000, 47,300, 2,300 kilojoules per kilogram. Okay, that means the water vapor in the combustion gases, when it is completely condensed, it will give you an additional 2300 kilojoules of heat per kilogram of gasoline. Okay.
Can I ask a
Any
question?
questions on heating value, lower heating value, higher heating value, even combustion efficiency?
Can I ask
Is
a
that
question?
correct? Yes.
After that slide, you in the combustion chamber, we use air too with gasoline. Why?
Air to burn it? Because air is the cheapest oxidizer. It has enough oxygen. It is a mixture of oxygen and nitrogen, and we get the gasoline. The nitrogen doesn't matter. Okay, it is not involved in the reaction. But let's say you have like 78% nitrogen here, right? All the nitrogen enters at 25 and leaves also at 25. So it doesn't make any difference. The oxygen is combined with gasoline. There is a chemical reaction there. Even if you have excess air, since everything is leaving at the same temperature, it doesn't matter. And this is what we do in real life. In the car engine, you know, we burn the fuel using air, right?
Mm-hmm. I got it. Thanks, sir.
Okay. Now for efficiency of heating equipment. In practice, you will see different definitions. Okay. One is AFUE, which is the annual fuel utilization efficiency. And the reason is that the combustion equipment often they don't run steadily. Let's say you have a heater in your house uses natural gas. Probably when the temperature in the room or the hot water system drops to a certain level, the heater will kick in, you will have combustion, and then when the water temperature rises to a certain level, then the heater will shut off, okay, and it will not burn any fuel until the water temperature drops again. Now, what happens now? The heater is hot, but it is losing now all the heat, and when the heater restarts, it will hit the equipment again, and that heat will be lost. So, you know, inefficiencies of this kind will be occurring. This is something more realistic in real life. And if the heater is, I think, designed to minimize the losses during those periods, then obviously it's a more efficient heater. The heating equipment, usually they list this number, okay? Meaning that they consider other things also. So keep that in mind. And new furnaces, heaters, they have efficiencies of over 96%. Sometimes they can go close to even 9%. Okay. Of course, they are the condensing heaters. That is, at the end, you have water leaving as liquid at room temperature. In the case of natural gas, it can make a difference of 10%, because our natural gas is what? Mostly hydrogen there, 1 carbon and 4 hydrogen. Natural gas, mostly methane, which is CH4 there. Now, other forms of efficiency, for example, in a power plant, okay, electric power plant. What do we have? We have a furnace where the fuel burns, and then we have a turbine where the steam energy is energy. A generator here, it converts mechanical energy to electrical energy, and they all have efficiencies. The generator efficiency is simply the amount of electricity generated relative to the amount of mechanical energy it receives from the turbine. And then the turbine, or this is the thermal efficiency for the entire system. How much, let's say, the heat, how much of the heat is converted to mechanical energy, let's say this part of the system. And then the boiler converts chemical energy into thermal energy. How efficient is that? So you have, like, combustion equipment or boiler efficiency, thermal efficiency, and generator efficiency. And then what is the overall efficiency? Then you multiply these three, okay? And it is called the overall efficiency. Therefore, in a power plant, the ultimate output is the electricity generated. How much electric power you supply to the grid, okay? And what is the energy input? You take the amount of fuel. It can be coal, it can be natural gas, it can be oil, whatever, or wood, if you want, and multiply that by higher heating value. Usually we use the higher heating value there, okay? So this is like the amount of chemical energy entering the system per unit time, and this is the amount of electrical energy leaving the system per unit time. That ratio is the overall efficiency. So efficiency, can be complex. And now, what is this overall efficiency? If you look at the car engines, it may be between 25 and 40%, okay, depending on whether they are gasoline or diesel. And if you look at the large power plants, like combined power plants with 1,000 megawatt, power output or more, can be like 60% there, okay? So it changes, but normally you will not see efficiencies much higher than this. That is, at the end, you lose a lot of resource, a lot of energy there. Okay, let's look at lighting as a special application. Now, what happens in a lamp? Typically, okay, let's say this is the light bulb, the old kind. Here we have, or it can be LED right now, whatever. We have electrical energy entering, right? Let's say in watts. And then what do we have? Light energy leaving, light. And we also have, if you touch these light bulbs, they are hot, right? So we also have heat. Now, what is the desired output here? This heat we don't care, so we want light. So the efficiency here will be the amount of energy leaving as light, okay, divided by the amount of energy entering as electricity. This is where we pay the money there, okay? And let's see how efficient they are. In the case of incandescent light bulbs, the regular old-fashioned ones, they are about 5%, okay? The old type, with this filament there, old types, they convert only 5% of the electricity to light. The rest is heat. So they are very inefficient, okay? The fluorescent ones, they are usually 4 or 5 times more efficient than this. So they can be like fluorescents 20–25%, okay? And then now we have LEDs, and LEDs can be like 25–30%. Or even higher. They are also improving. So you can see, the differences in efficiencies here. And the efficacy of lighting systems expressed as lumens per watt. This is a light unit there. Okay, let's compare them. This is the old type. Okay, you may not even have those anymore in your house, incandescent light bulbs. Let's say this is a 60 watt here. And it gives out, let's say, a certain amount of lumens. Let's say, what? 600 lumens. Okay. If you use a compact fluorescent light, which gives the same amount of light, let's say 600 lumens there, it will consume maybe just 14 watts instead of 60. Okay. And if you use an LED light, okay, again, giving out the same amount of light, lumens, it will consume, the number here is kind of low, but probably 8-10 watts, okay, for the same amount of light. So what is the message here? Obviously, you should not use this one, although it is maybe cheapest to buy. In the past, we would buy this one because LEDs were expensive, but nowadays LEDs are kind of reasonably priced. Therefore, when you need a light bulb, you are replacing an old one, typically you just purchase this one. And if you look at the lives, the incandescent light bulbs, they last about 1,000 hours. Then you have to replace them. Compact fluorescent lights about maybe 10,000 hours. Then they will burn out. But LEDs, they last like 25,000 hours, maybe more. Therefore, even though these LEDs are expensive, in the long run, they will pay for themselves because they last a long time, okay? And they are using a little electricity for the same amount of lighting. All right. Any questions on this, on lighting? Okay, no question. Then let's look at the cooking. You know, thermodynamics is a very practical course. You can use it everywhere. In your house, in your restaurant, whatever. Now let's say you are cooking using electricity, natural gas, LPG, whatever. How would you define efficiency? Again, what is the basic definition? Useful output, right? They are divided by input. Now, what is the useful output? The amount of heat which enters the pan here. Because you are cooking something, boiling water, doing other things, okay? How much of the heat enters the pan, okay? So it is the amount of energy right here entering the pan. Okay, what is the input? This is an electrical stove. The amount of electricity you consume, okay? And if this is, let's say, 5 kilowatts, and 3 units of it enters the pan, the rest is lost as, you know, heat to the outside from other places. Then what is the efficiency? Efficiency is energy utilized divided by energy supplied. So in this case, it is 60%. So just, you know, logic, using logic. What is useful here? At the end, I want thermal energy, obviously. And to get it, I use electricity. So take the ratio, see how efficient the system is. Okay. And if, let's say, you use high efficiency appliances, it means you will do whatever you are doing using less fuel or less electricity. As a result, you will produce less carbon dioxide, less nitrogen oxides and hydrocarbons, less carbon monoxide, and less sulfur dioxide. Okay, So you will pollute the environment less if you use efficient devices. Okay, which devices or which way of cooking is more efficient? Okay. Now let's say you are cooking something using different methods. Okay. So the amount of heat that you need is fixed. You will cook a certain size casserole there. You can do it using an electric oven. Okay, it can be turbo, and it can be convection or turbo oven. This is regular. It may be gas. You may use a frying pan, toaster oven, crock pot, or microwave oven. Now look at the results. The cost of cooking can range from 19 cents, okay, the cost of energy, to 3 cents. So the microwave oven is the most efficient because it converts electricity to microwaves, okay, and then when they hit the surface of the food, they are absorbed. If they hit the surface of the inner cavity of the oven, they are reflected until they are absorbed by the food. So microwave turns out to be very efficient. Normal electric ovens, not so efficient. If let's say you want to use the oven, then it is better to use the convection oven. They are also called turbo because they move the air around, so they cook faster in a short time. Instead of 1 hour, let's say 45 minutes. So the result is instead of 19 cents, you pay only 13 cents there. Okay. So by considering the efficiency of the process or equipment, you certainly can save money and consume less electricity. Okay, let's go through this example. Okay, we have an electric range and gas range, natural gas. What we will do is we will do the same cooking. Okay, maybe we will boil water, a certain amount of water, to the same temperature. Okay, the efficiency of electric ranges are typically high. In this case, it is given to be 73%. But for natural gas, first of all, the combustion efficiency, and then a lot of heat leaving before entering the pan. So typically they are like less than 50%. So in this case, 38%. Okay, and we have a 2 kilowatt electric burner. These are the prices. Okay, electricity 12 cents per kilowatt hour, natural gas $1.2 per term, and one term is 100,000 BTU in the US, or 105,000 kilojoules approximately. Okay. The question is, what is the unit cost of utilized energy? That is when you take the efficiency into account, which one is cheaper to cook with? Okay. Okay. First of all, electric heater, the burner consumes like 2 kilowatt of electrical energy, but efficiency is 73%. Okay, multiply those two, what do you get? 146 kilowatt. It means of the 2 kilowatt, 1.46 enters the food because the efficiency is 73%. Now, 1 kilowatt of electricity is 0.12 kilowatt hours per kilowatt hour, okay, dollars, and the efficiency is 0.73. Therefore, the cost is for 1 useful kilowatt hour, the cost is $0.164. in the case of electricity. In the case of natural gas, okay, we convert it to kilowatt hours. One term is 29.3 kilowatt hours, and the efficiency is 0.38. It is like, you know, you supply 3 units of chemical energy almost, and only 1 unit is useful. When you do that, you get 0.108 kilowatt hour. So this is the gas, natural gas, and this is the electricity. Now, although, and this is again for 1 kilowatt of useful energy for cooking. So although gas heater is less efficient, you know, 38%, since the gas prices are usually much lower than electricity, sometimes, you know, 1/3, sometimes 1/4, okay? As you see, for the same amount of useful heat, for 1 kilowatt hour of useful heat, if you use electricity, you will pay 0.164. If you use natural gas, you will pay 0.108. A saving of 52%. Okay? And this is typical. Even if, let's say, you do this using the values here you use in your house, in Ankara or wherever, you will find similar results. It is a natural gas typically will cost you half as much as electricity if you use a natural gas. But if you use LPG, liquefied petroleum gas, it will cost you twice as much as electricity and 4 times as much as natural gas. Okay. The funny thing is, most people use, you know, LPG tubes, right, for cooking. Some even think it is cheap. It is not. So if you have natural gas in your house, you should use it. And if not, you should use electricity. Otherwise, you will pay twice as much for the same cooking if you use LPG. Is that clear? Any questions on this? Okay, so it is clear. Now, before we go into the efficiency of mechanical and electrical devices, break of and then we will continue.